Israel is now a senior researcher at Weizmann Institute. So today we will discuss about interaction-induced localization in waveguide QED. Please.
Thank you so much. Grazie per avermi invitato. Prima volta, ok, non sono pronto per fare tutta la lezione in italiano e that will probably not be polite for all of us, but it's really a pleasure for me to be here, and it's recently, there are more and more very interesting works coming from Palermo, and it's my first time in the university, so I'm really happy to be able to talk here. I will talk about waveguide QED, which is also a big topic of interest by Francesco, by Federica, by Angela, who is not here, and hopefully by some of you. And I will talk for about 25 minutes maximum, but feel free to interrupt me with questions. I'm very used to be interrupted, and I have like 15 slides, and some of them I'm very happy to skip. So the problem that I will discuss, it's first based on my group research even some time ago, so some papers that were published like 4 or 5 years ago. And this was done mainly by Sasha Pashakinsky and Janet Dronk, and who were Sasha was a postdoc back at UFA Institute. He's now with Derek Chang in Spain, and Janet is now with Shanhui Fan in Stanford. So some theory part was done, and now in Weizmann we are trying to do experiment. And as usually when you try to do experiment, you get new theoretical challenges. So Matthias and Serge in Serge's lab, they're trying to make a sample. We are not there yet. I will not show any experimental results, but there are some new theoretical results we've done recently with Mayan, my last master student. So it's a talk on waveguide QED. I think here I even don't need a big introduction on waveguide QED. So basically, all I've been doing for last 7 years is interaction of arrays of atoms with photons in a waveguide, and this can be different waveguides, and this can be different atoms. Atoms can be superconducting qubits, can be quantum dots, can be natural atoms. Waveguides could be your fiber waveguide, this could be your photonic crystal waveguide. This could also be your microwave transmission lines if you are considering superconducting qubits. But for me today, the details of the waveguide, details of the platform are less important. I want to talk about some very basic effects in this system. So generally people think of waveguide QED as the, I don't know, a building block of your future quantum computer chip. You're going to have one chip here, one chip there, a waveguide connecting them, and we really need to know how to transfer quantum information. And all that, for me personally, it's more like a very interesting quantum simulator. And let me show what we are going to simulate. So today I will talk only about a two-body problem. And particularly, it will be a problem with two polaritons. So what are polaritons? Let me give you an introduction. So let's start just with an empty waveguide. So empty waveguide, which can host photons, and photons have a linear dispersion law. That's kind of maybe even too simple. So let's add atoms. And atoms have some resonance. So you have traveling photons, you have atoms, and atoms are not coupled to each other directly. So they are too far apart. There are no chemical couplings, no bonds, no van der Waals couplings. Atoms don't talk to each other by themselves. But what they can do, they can exchange photons. And it means that if I switch on the coupling, there will be an avoided crossing. So my atom modes and my photon modes, they will hybridize and they will form hybrid excitations, which are called polaritons. So there is an avoided crossing between this line, and as a result, you get two polariton branches. And this is still a single particle picture, but my atoms, my two-level atoms, are strongly anharmonic. It means that polaritons are not independent in this setting due to the anharmonic potential of the atom. So atom has only two levels, not infinite amount of levels. My polaritons will interact. And actually they exhibit like contact repulsion. So it's a problem with polaritons, two polaritons. This will be two lower branch polaritons in a finite array of identical atoms, finite periodic array, and my polaritons will interact with each other. And this is what I am going to study. So I want to study the two-body problem. I want to find all eigenstates of a finite array of two interacting polaritons. Polaritons interact because of anharmonic potential of the atom. Polaritons have this strange dispersion law. It starts here as a line and then it becomes flat. And this actually makes the problem very interesting. I think that typically people studied a lot interacting systems in 1D, right? From your Latinger liquid to your hardcore bosons, there are many models. But typically particles which are interacting in 1D have different dispersion law. So this polariton dispersion law is very strange. It's very non-parabolic. It starts as a line and then it gets flat, and here this part behaves, if you do some approximations, as -1 over k squared. So big part of this curve is actually hyperbola. So people don't know much about interactions of particles with this dispersion. And this is what is interesting for us. I will show you that in this system, the interactions can give rise to new correlated states of polaritons. How we solve it? We use a lot of approximations. So we use consider only two-level atoms. We use rotating wave approximation. Most of the talk today will be in Markovian approximation, where you can eliminate the photons, and then you have this effective Hamiltonian only for atomic excitations. And this effective Hamiltonian has long-range coupling because your atom can emit a photon which will travel far distance and then it will be reabsorbed. So it's not such an easy problem. Even for two polaritons, it's not such an easy problem. So what can you expect? You have still two interacting particles in a finite array in 1D. So let's start with a single excitation, just as a background. So all my atoms are the same. There is no disorder in the system. So I have some coupling, and if I have single excitation, it has nothing interesting to do. It will just, in a finite array, it will form a standing wave. So if I look for single polariton eigenstates, I expand them as superposition of excited states on all the atoms. So my psi n are amplitudes to excite atom number n. And all eigenstates are standing waves. These are well-known results. Yeah.
You assume that all the atoms are recurrent spaced.
Yeah, it's a periodic system, so I can use translational symmetry. And if I truncate it, my running waves become standing waves. Here, I did not cheat, but like I used some knowledge about boundary conditions that it's -1/2. But no, today no disorder. Otherwise, my standing waves will mix. So this is the same would happen for classical coupled pendulums. As long as you don't have any anharmonicity, any interaction, and it's a periodic system of equal oscillators or equal atoms. Only thing you can get for one excitation is a standing wave. The question is what should happen for two excitations? Because for two excitations, I cannot excite same atom twice, so anharmonicity should be important. And this is what we are going to focus on. And what can happen if you have two interacting particles in 1D? In principle, there are two solutions which are well known, again, for 100 years probably. First are called scattering states, and second are called bound states. So scattering states means that my two particles don't care about each other. They're kind of independent. They are both free to propagate over all the array. But other opportunities that they can meet each other and then they can form a bound pair so that their relative distance will be small. But then they can propagate together along the array, and then they can form like they can be quantized as a whole, so they can form a standing wave, but of a pair. So this pair can propagate and they are correlated. So, and this is what was known before our research. So if you have two particles in 1D, either they are uncorrelated or almost uncorrelated, or they form a bound pair and they travel together. The question is, can you get something else? Are there other correlated states, other strongly correlated states of two particles beyond bound states?
But by moving together, we in the real space, right?
In the real space. So you could think of your two polarity wave function as something, I think I have some space here. So psi nm is exponent n minus m, where these are coordinates, and then there will be something depending like on their translational motion, like cosine n plus m over 2k. So this is their motion of the center of mass, and the relative motion is constrained. And this is what we are not interested in today. So the question is, can you get anything beyond this? And the answer is, well, I'm here, so it has to be something. So first time we saw it, so what we did, we solved the two-particle Schrödinger equation, effective Schrödinger equation, and we calculated the joint probability to excite two atoms. So here I have 50 atoms, don't tell it to experimentalists, let's draw 50 qubit array, and they will, we are now building a setup with 4, so it's a bit less than 50, maybe 6, but still like not 50 qubits. We are not in IBM. So let's plot the joint probability to excite two atoms. So this is coordinate of excitation number 1, this is coordinate of excitation number 2, and color means probability to excite both of them. And if you have a scattering state, it would be like waves in the square bucket. So it would be some product of two cosine functions, like some cosine along x and cosine along y. And instead we got this very strange cross. So it looks like along this direction you have a standing wave. Because you see here it's a maximum, minimum, maximum. Something is 0 here, and then again maximum. And in this direction it's strongly localized. So it looks like one particle is moving or forming a standing wave and another is localized. So if you think of this family analogy, it's one partner who has to stay at home and care for the baby, something which is close to my heart at the moment, and another one has to go to work, but it's a modern family, so my two polarities are indistinguishable. So like both of them have to share the burden and to go to work and to care at home. So it's a state like that. So mathematically you could write this wave function as a product of something localized and something which is a cosine. It's a product, so it's a superposition of states where one polarity is a standing wave and another one is strongly localized, just on one side. It's a very strange correlated state. You don't get any correlations without interaction, but with interaction you can get it. And super strange, and we first thought it's an numerical error. And then we got some interpretations, so you could think of it as a self-induced optical trap. Yeah.
Can you say how you found it? Because you said you saw the Schelling algorithm in general, which includes, I guess, the previous long cases.
Yeah, absolutely. So we also find this. So we substitute like this and that in the two-particle Hamiltonian. Then we find like for 50 atoms, 50 squared states with two excitations. And some of them are scattering states, some of them are bound states, and then some of them are very strange. And then we try to analyze like these strange states. So some of them are chaotic. I have somewhere a picture of everything you can get. So most of them, if I'm being completely honest, most of them, parametrically, most of them are chaotic. Because it's a non-integrable problem with interaction and you can get quantum chaos. But today I don't want to talk about quantum chaos. So I'm saying that so some of them, it's like you can get very diverse types of states, but some of them, like n, if you have n qubits, you have n states, and probably on the order of n, probably even more, will be of this type. And the very fact that you can get something like that was a surprise, because it's a strongly correlated state, and it's not a bound state. And then we did some analytics, and we can find like this analytically, and we can also give a qualitative interpretation. So this is sort of a interaction-induced, yeah.
How the localization length of the confined particle, how does the localization length depend on parameters?
It's on the order of unity. It's super, like, it's somehow it's basically it's set to be the scaling of the lattice. So it's super well localized. So for one of them is delocalized, and one of them is localized at the scale of one side. And this is only if you switch on interaction. If you don't switch on interaction, you don't get any localization. So
it's like whatever the interaction strength?
No, interaction strength has to be larger than coupling to the waveguide. It has to be strong enough. Once interaction is much larger than the coupling to the waveguide, once your atoms are unharmonic enough, you get this state. Once the atoms are unharmonic enough, so then you get this. As soon as your unharmonicity is at the level of coupling to the waveguide.
So you're considering just the effective outcome coming to the coupling, for example, the atom to the waveguide, right?
Yeah, we take this effective Hamiltonian and we look at the eigenstates in the double excited sector.
You're talking about interaction in this interaction.
Interaction happens because sigma squared is 0. So you cannot have two polarities at one point. So it's like, it's a contact repulsion. And this contact repulsion, if I switch it off, then I don't get any localization. If I keep it, then I... There will be, I'm going to show you probably something like that. So this is not the only weird state we get. So it's like, basically you can have more than one node of the standing wave. And in every node or in every anti-node, you can get localization. So here, I just suggest to think of it as a self-induced optical trap. So what is an optical trap? You take a laser and in the maximum of electric field, you trap a particle. Here, it's like a self-induced trap, because you have two polarities which interact, and polarity 1 traps polarity 2, and at the same time, polarity 2 traps polarity 1. It happens only in a finite system because you need to have a standing wave. But as long as you truncate your array, you will have standing waves, and then you will get this very strange eigenspace. Yeah, please.
Actually, am I correct in saying that here particle 2, because your interactions were recursive, right? So your particle 2 has to sit in at one of the nodes of the standing wave?
Yeah, or in one of the antinodes.
Okay. And then one question is, couldn't you also then have more nodes or more complex standing wave with more nodes?
Yes, just wait one slide. Absolutely. So what happened in the other way to think of it in the Fourier space, so standing wave corresponds to polarity somewhere here, and localized excitation corresponds to polarity somewhere in this flat region of dispersion. So the dispersion has a big flat region. Here it's very flat, and if it's very flat, something is very easy to be localized. So this dispersion is super interesting. It has a fast part and the flat part. So you kind of have two species of polaritons in the same band. And fast polaritons act as optical traps for slow polaritons. So, and then like exactly the question is, what happens if you get more nodes? And you can do some math and you can actually do some analytics, and you have for these two particles, assuming that one of them is a standing wave, and you can get effective equation for polariton in the potential of the standing wave. So, like your first polariton experiences a lattice, and it also experiences a standing wave from another polarity. And this is an equation that we know very well in physics. So it's an equation, if I write it exactly, it's an equation with some lattice periodicity and with some extra cosine potential. So such equations are known in tight binding. It's very similar to this Harper model for electron in a magnetic field, or Abré-Adré model. So Abré-Adré model describes like a tight binding model with identical site, and on top you get a periodic modulation, which is either due to external potential or due to magnetic field. So here you have polarity on a lattice, and in addition to that you get the modulation because of another polarity. So this standing wave is now not your external magnetic field, it's just another polarity. And again, like it's always important, I want to stress it, it's a self-induced model. So when I'm saying polarity 1 experiences the wave from polarity 2, it's vice versa as well. So, and then, okay, so this is our equation. It reminds equation for an electron on a square lattice and magnetic field. So then here you know what to expect. You can expect Landau levels, you can also expect H states. So which means that here, if you solve it, you also get eigenstates like that. So here one of polarities is at the H, and another one forms a standing wave. So this is super weird, because typically in order to get an H state, well, I've been in this business for like 12, 13 years already of topological H states of photons or whatever. So you always need to add some modulation, some SSH type modulation, some time-dependent Flaquet modulation, some magnetic field. You need to add something deliberate, some spin-orbit interaction, so pick up whatever is your favorite type of thing to get an H state. Here you just have a lattice with one atom per unit cell. You don't have any external modulation, you just have two particles. And you get this for free because of their interaction, which is the simplest one, contact repulsion, and because of the non-parabolic dispersion of polaritons. So non-parabolic dispersion of polaritons gives rise to weird correlations. And also you get bulk states which look like that. Yeah.
Typically to that edge state, to break time reversal symmetry.
No, this one doesn't, but it's not protected against anything. That's like, it's of course it's not protected. If my atoms will be different, I will destroy.
Okay.
I think it's protected against a little bit, like protected if you move the atoms. That's not so important. So non-periodicity of array, if the coordinates are non-periodic, that's okay. If the frequencies are different, then no. It's most of your photonic topological edge states, like you take some material and drill holes in a smart way. Usually they are not protected against anything. So this one is also not protected against anything, almost, but the fact that it's there is super weird. Because you get it kind of for free, we never wanted to have it. And it's interesting just because of your non-parabolic polarity dispersion in the waveguide QED, and because of interaction you get this.
Can you explain what are these edge states that are built? So we started with, if I understand correctly, an array of 50 atoms, right?
Yeah.
And you were getting a superposition between the standing wave and the bound state.
Yeah, so wave function could look like that. Okay. So it's a two polarity wave function depending on two coordinates. So x and y. My two polarities are indistinguishable, so it has to be symmetrical in x and y. And it looks like a superposition of a standing wave and something which is localized at the edge.
Yes.
And the other way around. It's a solution of this.
Yes, and then I would, maybe I missed out the mapping work with, you said that there is this cosine-shaped stuff that it's reminding of the modulation.
So this cosine, the standing wave acts as a modulation as a magnetic field. Okay. So one polarity forms a standing wave and provides a periodic additional potential to another polarity. So that is, I will try to wrap up. Now, this is our prediction that you get in waveguide QED new type of correlated states of even two particles. It has not been observed so far. We are hope to observe it like next year. We're now building a sample and we have a lot of challenges because it's just one state out of many double excited states. So not one state, but several. So then you need to build a cavity around to have some selectivity to excite it. So we decided with experimentalists, okay, let's build a cavity. Then, okay, you want to develop some theory how to describe it. But once you build the cavity, it becomes non-Markovian immediately. Then, okay, like half of theoretical approaches I showed you, they just don't work. You need a cavity for spectral selectivity, but then you need to think how you are going to describe it. And then we had some approach how to get the same results in a non-Markovian way. These are results from like several months ago. And then we hope, so these are some of the calculations just for 4 qubits, but they take into account some realistic excitation, they take into account the cavity, they take into account all the non-Markovian processes, and we really hope to see this. So here instead of 50, you just have 1, 2, 3, 4, but still the effect is pretty robust. So we hope to see that one polarity is at the center and another one is at the edge, or vice versa. And well, I don't know. It's like experiment is challenging, but at least.
Can you say how the experimental setup would like?
So it's superconducting qubits. So it's superconducting qubits coupled to transmission line, but we also will put 2 mirrors. So the only special thing is that you need spectral selectivity, you need to increase lifetime so that you can selectively spectrally excite different states, and for that we decided to build a cavity. But then, like, for experimentalists, it's very easy. For theories, as soon as you put around the cavity, you get all the problems. It's strong coupling, and if it's strong coupling, it's non-Markovian, and is it waveguide QED, is it cavity QED? Now, it's a lot of even technical problems, but somehow we solved them, and we hope that in the foreseeable future we will be able to do excitation and quantum tomography of array with several qubits, and then we'll see something like that. I don't know, like you never know, but preliminary we have some samples at the moment, and we have some promising calculations. So this is a summary of the talk. So this was published some time ago, and this is something we are actively working on. So I guess the main take-home message is that in waveguide QED, you get for free very strange two-particle correlations, even if you don't want them. It's always on the order of UniPa. Somehow we have a, let me check if I have it here. So you can do some continuum model analysis, and like you can solve equation for localization could be like that. If you, and this comes from the polarity and dispersion. And this is a very weird equation because it has no scaling. Like some people told me it has some connection to supersymmetry, I don't know. So it's, if you try to do quasi-classics on this equation, you find out that all solutions are the same. So this is a very strange type of Schrödinger equation. This is the one which describes localization. So in continuum approximation, all eigenstates are the same. It means that the localization length will be some cutoff, and the cutoff is the lattice size. So because of the polarity and dispersion, it kind of, by having this very big flat part, it favors localization lengths on the order of unity.
So, shouldn't I just think about this? Sorry, because you told us before that some solutions should be solved and one part of this so one part will stay and the other one sitting in the region, right? Shouldn't just one think about the state if the localized particle just so just as a special case with this localized.
I think you could, but it's the same as in, in your quantum Hall model. If you consider the Harker equation for electron on this one, for electron in a lattice in a magnetic field, you also get bulk states, you get H states, you get Hofstadter butterfly. So you could have interpretation just like that. So it's correct, I think. It's you could describe it on a high level with stock of Chern numbers and topological stuff, but also you could have a very simple interpretation, and I think both of them are correct. So yeah, you could. Here we also have, if we really, I decided not to include in the main part of the talk, but we even have something like a Hofstadter butterfly here. If we, this is your effective magnetic field, which is the wave vector of the standing wave, and this is your energy, and if you properly analyze your spectrum, you could get here even something like a sort of a Hofstadter butterfly, without any magnetic field, without anything, just because of this weird interaction.
More questions? You stress that this stuff depends a lot on having a flat, very flat part of the dispersion on a very steep one. I was wondering if you have another dispersion along with this, a flat part and a very steep part, but a different dependence on scale. I don't know if this is possible.
It is, I think, one of.
You think this would be enough, but a different scaling?
I think it should be enough. I think one of so my former postdoc in one, I think they even did it like just cosine dispersion tight binding is not enough.
Yeah.
But if you add probably second and third neighbors, you can make it non-parabolic enough to get this. So it's just enough to have a relatively steep part and a relatively flat. Yeah, probably third with some fine tuning should be enough. So we even checked it.
Okay. Any more questions? Not. Let's then touch again.
So I should stop. So I don't know what is the procedure. I'm afraid.